Hey everybody, I am going to be looking at gases today, and we are going to look at how particles can move at different speeds in a container and what distribution it's kind of set up to be. So I'm going to put some particles here, pump some gas in here, and I have some heavy particles. What I want you to pay attention to is the graph on the left-hand side here. So if I have a certain number of particles in this container, you can see here, some particles are moving, they don't all move the same speed. So I know that in general, when we heat up a gas, the particles move faster. When we cool them down, they move slower. But as you can see, different particles have different speeds. So this, let's say if I follow this particle here, this one's really slow, but I have some particles that are moving faster, and then they change speeds because they hit the walls or they interact with one another. And so on the left-hand side, this is what we call a distribution graph. The average speed's up here. So it says, 450 meters per second. But this graph tells me that if I have some particles that are moving slow, so on the left side of the graph, the slow speed, there's a couple particles that are moving slow. So this is changing periodically because they're not all going to stay the same speed. But then, but as I move to the right, as I go faster, there's a big group of particles that are moving a little faster. There's another group of particles that are moving kind of a little faster. But then as you go faster and faster, there's fewer and fewer, because the left side of this chart tells me that the number of particles, that is the total number of it's kind of a distribution graph. So as I go from left to right on the graph, there's a few number, and then it goes higher. There's a little bit more, and then there's fewer, and there's fewer, and there's fewer. And then if I look out here, there is no particles that are really fast. Okay, so the graph kind of goes up like this, comes down like this, and this is called a distribution. And the area under the graph, what I'm going to do is I'm going to heat this up now. So as I heat it up, we know that the particles are going to go faster, but they don't all shift faster as together, right? Because it doesn't work like that. So I'm going to heat this up, and we'll just watch to see what happens with the distribution of the graph. So I'm heat it up, and you can see now the peak of the graph is sort of shifting, but you can also see that it gets more spread out. So you can see that instead of having a really sharp peak in the beginning and drifting off, it is now spreading out and all becoming a little bit lower. So this, if I look at this right here now, this has particles that are not as many here, and the peak is not as high, but it's more spread out over the range of speeds. And so what happens is the area under the graph, all the little tick marks that you're counting for the distribution, the number is the same. The area under the graph is the same, but it's now spread out more as you heat it up. Okay, so that is called, I'll write it down for you, it's called the Maxwell Boltzmann distribution. It describes how particles are the distribution of particles as I cool them down or heat them up. And then as you keep heating up, it keeps spreading out. So I keep heating this up, and you can see how it spreads out. You can see how it keeps spreading out, spreading out, spreading out. So it's going to go more spread out, not as many and so I have some that are really fast, some that are really slow, and then everything's kind of in between, okay? And if I cool down, then it starts shifting back to, now you can see it's shifting back to a lower speed, and now I have a higher, they're all more concentrated at certain speeds. Okay, I'm going to add some light particles now. So we'll see what happens when I have light particles at the same temperature. So remember, I'm going to go ahead and add, oh, that's too many. So let's say 100 particles, light particles. And now we can see that, let's see here. Okay, so I'm going to try to see if there's a way that I can, too many things here. So if I look at the light particles, even though they're at the same temperature, you can see that the speed of them, they're going to go faster, right? Because they're lighter. And so the kinetic energy is got to be the same. So if I look at kinetic energy of the red and the blue, they should be about the same. But the speed is going to be faster for the lighter ones because they just are lighter. So, but if you look at how they're distributed, that flatter distribution you can see for the lighter particles is happening. So the overall kinetic energy of the two heavy and light particles are about the same because the temperature is the same. So we say average kinetic energy is the same, but the speed distribution is different for a lighter gas because it is going to be spread out more. Things are going a little faster. So I'm going to try to get this down in some notes for you, and we'll do that in just a second. So here is the kind of the gist of the Maxwell Boltzmann distribution. So this is the name of the two people that kind of came up with this idea. And just to summarize, so you should jot this down. If I have a distribution graph and kind of like this, okay? Now, in the simulation, there was this number of particles on the y-axis and then the speed on the x-axis. And if I had this many particles for this speed and this many particles for this speed, this many particles for this speed, and so on, and I actually counted the speeds of molecules and the number of molecules for any given moment in time, that's what this is showing. So it's kind of it's called a histogram, where you're counting things and you're just tallying them up and seeing, well, this has this many particles, this one. So this is not the fastest speed, right? Speed goes this way, but this is the most probable. So this area right here, the most number of particles, or the most probable number of particles, is going to be at this number of thing right here, okay? So this is the most probable, or the most number, the biggest number. But that's the speed, kind of the average speed. Now, on average, it's going to be right around here, but there's a distribution. So if I take the same gas and I heat it to different temperatures, what we saw was that this gas, the whole thing doesn't shift equally. It starts going like this. So it spreads out more. So this is a little higher temperature. And you can see that the number of particles is less concentrated at any given speed, but it's spread out more. Or if I heat it up even more, it spreads out like this, and like this, and like this. So I keep heating up, and so on. So what happens is the area under the curve stays the same. So the area under the curve is the same. But as I heat it up, it just keeps shifting over and over to the right and spreading out. So there's a bigger distribution of particles. The other scenario we looked at was different types of gases at the same temperature. So this shows here, I have two different gases at the same temperature. Let's say I have this graph like this. Okay, this is a heavy gas. Well, if I have a lighter gas at the same temperature, it's not going to have the same distribution. It's going to be spread out more like this. So this is a lighter gas. Or if I have even lighter, maybe even spread out more. And why is that? Well, remember, light gases have, so this is the lightest. Light gases have more motion because they move faster, However, the kinetic energy, or I'll say average kinetic energy of all the gases is the same, okay? And how is that possible? Because we learned last year that, well, if the kinetic energy is the same, they should move about the same. I kind of lied to you. So if I have a really heavy gas, it's like this. What the truth of the matter is that kinetic energy or average kinetic energy depends only on temperature. Okay, so it is these two things, and we learned that last year. These two things are directly connected. But kinetic energy of a particle is equal to 1/2 mv squared. This is of a particle. Okay, so for one particle, this is mass, and this is velocity, which is speed. Okay, so if I have a heavy particle, if this mass is big, then the velocity is going to be much smaller because heavy particles don't move as fast. But if I have kinetic energy of a particle that is light and the kinetic energy is the same, well, let's say that this mass here is small. So what happens if it was small? For it to be the same kinetic energy, small mass, that means the velocity has to be very big to make the kinetic energy the same. So small particles move faster. That's why this is distribution here. Heavy particles move really slow, but they all have the same average kinetic energy because they are at the same temperature. So that's kind of be really important in understanding these types of problems.